me the opportunity to present this work in here. And this is a work done it has been done in collaboration with Tony Pic and Ignacy Rosell from Valencia. And this is just a quick outline of the talk. First, I will provide the motivation of the standard electroweak symmetry breaking and the computation of the S parameter. And in the second part, the effective Lagrangian that we will use and the computation of the relevant correlator. A crucial detail will be that we will impose high energy constraints, and finally we'll see some numbers. So what we have performed is the one-loop calculation of the oblique S parameter, okay, with Higgsless models for electroweak symmetry breaking. Why? Well, if eventually at the end of the day there is no Higgs, well, one should look for alternative ways for mass generation in like strongly coupled Higgsless models. And the way how we have performed this computation is through an effective approach where, taking into account that the electroweak symmetry breaking is actually pretty similar to that you find in QCD for chiral symmetry breaking, okay, where it is described through where the Goldstone interaction is described through chiral perturbation theory. We use also that, and take into account that many strongly coupled Higgsless models also produce resonances, like in QCD, and therefore we think that it's proper also to use the theory that we use in QCD. Sometimes, some people here there could be also the discussion, which is resonance chiral theory. And we will build the Lagrangian with at most two derivatives, and we will impose also further short distance conditions. And we'll use this and we'll plug it in the dispersive representation from Peskin and Takeuchi. Why Higgsless electrowheel resonance models in string phenomenology? Well, essentially because many string theory constructions contain a tower of vector and axial vector resonances, which is what really matters in this observable. And this is actually the only place where you see the word string in this talk. So actually, all I want is the tower of resonances that, for instance, you also have in holographic constructions. So we look at the strongly coupled models, Higgsless, where you have a non-perturbative electroweak symmetry breaking, and instead of one has compound resonance states, instead of the.
So it's like a technical type model?
Yeah, for instance. But.
And are you compatible with 125 GeV?
125 GeV for the vector? No, but well. I won't be compatible, but let's wait for the for the end of the game. Far from compatible. Okay, so well, there are many options, even many technical. So essentially, what we do is, okay, we have electroweak symmetry breaking, similar to chiral symmetry breaking, okay, of SU2 left and SU2 right into the custodial group. And actually, at low energies, it has the same effective field. One has the same effective field theory pion Lagrangian to describe the interactions of the Goldstone, similar to chiral perturbation theory. And in particular, one of these ways of breaking the symmetry is the standard model, where at energies much lower than the Higgs mass, well, one has the operators of chiral symmetry breaking, but instead of F pi, what you have is the V from the electroweak sector. Therefore, we'll construct the effective field theory for the Goldstones, where the standard model gauge symmetry is non-linearly realized, plus the latest resonances from the strongly coupled Higgsless models. We'll make a construction similar to resonance chiral theory in QCD. And well, incidentally, if one performs the most naive rescaling from QCD to the electroweak scales. This is from f pi of 90 MeV to V of 246 TeV, and we just move everything. The masses go to the range of the first resonances would go to the range of the TeV, but okay. Remember this order of magnitude when we go to the result. But indeed, I'm not going to use this kind of game at all during the calculation. And then the last, what we are actually doing is estimating the S parameter, which is essentially equivalent to the determination of the chiral perturbation theory low energy constant, the L10, okay, in KPT and in resonance chiral theory. So the precise definition of this electroweak precision observable is just, well, it's given by this W3B correlator, okay, at low energies, and indeed one subtracts the standard model, the theoretical standard model contribution from the in the definition of the S parameter. Okay, so in such a way that what you see is deviations from the standard model. Peskin and Takeuchi actually were able to express this in terms of a dispersive representation, where actually all you need to know is the spectral function of this correlator, and thanks to that, okay, of your theory, and you subtract the standard model, and thanks to that you can actually extract the S parameter. But one has to keep, okay, one has to, I mean, just looking at this expression, one has to take into account, well, first two important, well, okay, one has to take into account two important things. The first thing is that the spectral function must fulfill vanishing behavior at high energies, at short distances. And the other important thing is that in the same way as the L10 low energy constant in chiral perturbation theory is always defined for some arbitrary renormalization scale mu, S is always defined for an arbitrary reference scale mh. Okay, well. And thus we construct our effective field theory with at most two derivatives, and later we will add some further short distance information, where we include the standard model gauge bosons, the goldstones, and the first vector and axial vector resonances. Okay, then we have operators without resonances, operators, the general set of operators with one resonance field, and also operators with two resonance fields. But actually, we, at the end of the day, we'll see that only two combinations of couplings enter in the observable. And counting the number of parameters that, I mean, after doing the computation, when you count the number of parameters of your that enter in your determination, we have 7 resonance parameters. And here, well, the high energy constraints will play a crucial role. Okay, at Lane order, the thing is pretty trivial. One has the 3-0 correlator, okay, and then the 3 level exchanges, and therefore at low energies one has the usual formula. At next to Lane order, you have all these one loop diagrams, all these possible one loop diagrams, and thanks to a one subtracted dispersive relation, where we plug in the 3 level and 1 loop spectral functions, it's possible to recover the full correlator. Okay, and indeed we consider the pi cut, the vector pi cut, axial pi cut, and actually as you go to higher and higher thresholds, the contributions to the S parameter, which is more and more suppressed in the dispersive integral. And then this expression actually takes this form, where you have the renormalized 3 level contributions plus the absorptive contributions from one loop diagrams. And when you go to low energies, okay, this term gives this term, and you have a contribution from the absorptive one-loop diagrams. Okay, and now the other, one of the crucial points is the high energy constraints. So the thing is that in contrast with QCD, we ignore what is the underlying theory. So what we do is we work with a series of hypotheses, and from those hypotheses, we extract conclusions, and so this is actually what we do. So essentially, if you look at the operator product expansion at short distances for the 3-0 correlator, for the W3B correlator, depending on the dimension of the first operator that you have in the operator product expansion, if the dimension of the operator is larger than 2, as it happens in the Technicolor models, then you have that your spectral function fulfills the first Weinberg-Sum rules. And in the case when the dimension of the operator is larger than 4, then you also have, like in asymptotically free models, you also have the second Weinberg-Sum rule. So therefore, at leading order, at tree level, you will have 1 or 2 constraints depending on whether you take the first Weinberg-Sum rules or the 2 Weinberg-Sum rules. For the imaginary part, the analysis of the spectral function at next to leading order will give us 3 or 4 constraints depending on if we take 1 or 2 Weinberg-Sum rules, and the analysis of the real part at next to leading order will help us to determine and to constrain the renormalized resonance couplings. And in addition, in the bibliography you may find different constraints that the people study, like what is many times called the unitarity bound, which refers to the WW scattering, or the pi vector form factor. The constraint that this form factor vanishes, or the pi gamma axial form factor, that the requirement that this constraint vanishes. So if we now count all the constraints that we are able to gather, we can gather up to 7 constraints, depending on whether you take 2 Weinberg-Sum rules or just 1 in your hypothesis. And in principle, it's not possible to fulfill all the constraints at the same time, because remember that we are also cutting we're cutting the tower of resonances, so it's impossible to really fulfill everything exactly. So what we do is we play with sets of constraints, and we check that the other constraints are approximately fulfilled, and that the results the outcomes that comes from the different analyses are consistent with each other. So then, what happens with the phenomenology? Okay, so this is the experimental number, okay, for this reference scale of the Higgs, and if you take the leading order result, actually, with 2 Weinberg-Sum rules, you have this nice prediction. And actually, if you only had 1 Weinberg-Sum rule, but still you have the hierarchy of the axial, of the first axial being heavier than the vector, you can still derive a lower bound for the S parameter. So essentially, you can predict the lower curve, and your S parameter would be in the shaded region, the shaded area. So essentially, the prediction that you have at leading order is that the mass of the vector must be over the 1.5 TeV at the 3 sigma level. What happens if then people try to lower this scale by analyzing the one loop corrections. So what happens if you have 2 Weinberg-Sum rules? Okay, if you consider the first and second Weinberg-Sum rule at leading order and next to leading order, you get 6 constraints, and then the only free parameter that remains is the mass of the vector, And this leads to 8 solutions, which I plot here. And indeed, among these solutions, there are some solutions which are completely crazy, even if they look pretty much the same, and the predictions are pretty much the same. What we consider the actually good solutions are only 2 of them, which are compatible with the vector form factor, axial form factor, and scattering constraints, which suffer small deviations of the order of 10% for these constraints. Okay, and if you use alternative sets of constraints from the first and second, from the first and second Weinbergson rules and the vector form factor and four factors constraints, you get even more stringent bound. But if you remain, okay, if you keep the least stringent constraint, the most you can do is to reach your lower bound for MV up to 1.8 TeV at 3 sigma. Okay, if you remove the second Weinbergson rule, now you can already. 1 minute. Okay, you can fulfill the Weinbergson rule with only the pi, and actually the expression in the case that MA is larger than MB, you can extract a lower bound, and indeed in this case the expression is extremely simple. Okay, you can very clearly see the structure of the corrections, and again the bound is the same as before. And if you add also the next threshold, the contributions from the next threshold from V pi and A pi, essentially you get 2 solutions, okay, or 2 families of solutions. The green ones, where if you increase the ratio between axial and vector, you go up, and the red one, that if you increase the ratio of axial over vector, you go down. So from the green ones, you get again the same lower bound, and for the red one, in principle, you could really decrease the lower bound up to a few GeV, but the price you have to pay is really big. Well, first there are huge violations of the second Weinbergson rule, which is not really a big problem because it's not the hypothesis you do here. But in addition, you have huge corrections to the first Weinbergson rule and next to in order, large splitting between axial and vector, and even in this case, the axial never goes below the 1 TeV. So, then conclusions. We have performed improvements with respect to previous next to in order calculations. We use dispersive calculation with no unphysical ultraviolet cutoffs, more general Lagrangian, introducing short distance information, and from the analysis of leading order and next to leading order with different hypotheses, the result is that in general the higher resonance mass scale is always well beyond the 1 TeV, and future work, oblique T parameter, and possibly find some dispersive representation. And sorry for the extra minute.
I didn't understand at the end. So you say you're not compatible with Higgs at 125.
No. Okay. Sorry. No. No, I thought you were talking about vectors in the GeV in the GeV range. Right. I mean the 100 GeV. So
is it compatible with the Higgs at 125?
Actually, the thing is that all this is thought for Higgsless. Right. So the regularization. Okay, in the standard model, if you remember this dispersive integral, the behavior of the spectral function goes to 0 because of a precise cancellation between the Goldstone channel and the pi channel and the pi Higgs channel. At high energies, they cancel each other. If you don't have this, if you don't have the Goldstone channel, if you don't have the Higgs channel, then this regularization of the behavior at high energies needs to happen in some other way. What happens if there is Higgs? Then?
No, I mean, are you compatible with the resonance at 125 or not? I mean, you know, it's
but you mean a scalar resonance?
No, it's a resonance. Whatever they observe, the resonance resonance at 125 GeV. Are you compatible with it or not? I mean, you know, this is the data. Are you compatible with the data or not? I mean, you know.
Yes, but the data. Okay,
I
but
mean,
I'm
then-
asking
then
you.
there is the issue of interpretation of the data. So you can interpret it as a fundamental scalar, or you can, in your scenario, interpret it at the bound state. So,
Okay, so let me tell you. Let me repeat it. All this is assuming that there is no scalar state.
Yeah, no, I understand that.
Okay,
but
if
is
they-
it
if they're-
compatible with resonance at 125 GeV?
Okay, if there were a scalar at 125 GeV,
Yeah.
okay, we could still think of, we'd have to modify this
Alright.
in the sense of there could be the two scenarios where you have the resonances, where the cancellation at high energies could happen between an interplay of the pi channel and the Goldstone, and the Higgs pi channel. So
Okay, let's move on to the next speaker. So thank you very much again.